perfect.
So our final speaker for the parallel session is Ronnie. He'll tell us about entanglement rényi, entropies, and celestial holography.
Thank you. So let me begin by thanking the organizers. I'm very grateful to be able to speak at this nice conference. So I'm going to tell you about some work that I've been doing with these people here that I'm very hopeful will appear on the archive this month. So hopefully you can read more about it if you're interested. Okay. So the setting is celestial holography, perhaps unsurprisingly in this parallel session. And so just to start out with a quick review of the asymptotic symmetries of flat space. So I'm going to always imagine I'm in some asymptotically flat space-time, so roughly my metric will look like Minkowski at large radial coordinate r plus some corrections signified by these dot dot dots. And here I'm using some complex angular coordinates on the sphere in these spherical coordinates. And so the symmetries that preserve this leading order form at large r are the asymptotic symmetries, and they're super translations and super rotations. And I'm really going to focus on super rotations in this talk, which are parameterized by a holomorphic function of this angular coordinate z. I call it w. And so at leading order at large r, z just goes to this holomorphic function, and then there's also some rescaling of these other coordinates, plus corrections. And when this holomorphic function is a Mobius transformation, then this is just a Lorentz transformation of some sort. But you can also consider, for example, singular 2D conformal transformations. And this sort of leads to this relation between 4D flat space scattering amplitudes. If you write them in the right basis, they look like correlation functions in some 2D CFT. And this is the idea behind this notion of celestial holography, that perhaps you can find some two-dimensional conformal field theory that would reproduce 4D flat space scattering amplitudes for you. Okay. But in this talk, I want to go beyond amplitudes and try to expand this celestial holographic dictionary with entanglement entropy. Okay. So to start off, I want to consider a particular superrotation, which is singular, and it looks like this. So it's singular at these 2 points, z1 and z2, and it's also parameterized by some number n. And if you do this, and you perform the superrotation, Minkowski space turns into this complicated-looking metric here, which has been known, at least since the 90s, to be the metric of a cosmic string, or the tension determined by this n. And you see a leading order at large r, this just looks like the Minkowski metric that I wrote down before, but you have subleading corrections on the spherical legs of this metric, and they encode some conical singularity in the bulk. It's related by a coordinate transformation to this metric, which you might more readily recognize as a cosmic string. But the key point about this complicated metric is that at large r, you have the Minkowski metric, so it's asymptotically flat. Okay. And now for something completely different. So entanglement entropy in quantum systems is defined by first taking a Hilbert space, which you divide into a product of two factors, A and B. In the QFT, we typically take these two factors to be the states on two different regions of space, which I'll always assume. And then if you take the density matrix rho, defining the states on the full system, and then you trace out the degrees of freedom on the subspace B, you get what's called the reduced density matrix, and the entanglement entropy of A with B is the Neumann entropy of this reduced density matrix.
Just a comment. In quantum field theory, it's not possible to factorize the Hilbert space.
No. Modulo some subtleties, yes, that's true. Yeah. Okay, but because of this logarithm, it's difficult to write down, well, you can't directly write down a path integral formulation of this entanglement entropy. And so one approach you can take is what's called the replica trick, the first step of which is to define these Rényi entropies, which are essentially the log of the trace of the reduced density matrix raised to some power. And the entanglement entropy is the n goes to 1 limit of this. And it turns out that the Rényi entropy you can write as essentially the partition function on an n-sheeted manifold, which is sewn together cyclically along these regions that you're using to define the entanglement entropy. So I've drawn a cartoon here. So this little letterbox is supposed to be my region A that I want to compute entanglement entropy for. I have, in this case, 3 copies of my manifold, so this would be for n equals 3, and I just sew each copy together like this. Okay. But it's still very hard to compute the path integral on such a manifold, but fortunately in 2D CFT you can use the power of two-dimensional conformal symmetry to simplify your life a bit. This was worked out by Calabrese and Carde 20 years ago. So I'm going to imagine I want to compute the entanglement entropy of an interval, just a single line essentially in my two-dimensional CFT. And I can perform, so the endpoints of the line is Z1 and Z2, I can perform a conformal transformation called the uniformization map, which is singular at these 2 points. and this maps my n-sheeted replica manifold just to a single complex plane. And the key point I want to draw your attention to is that this uniformization map is exactly the same as the superrotation that introduces a cosmic string into Minkowski space. And the task of the rest of this talk is to make this connection precise. But just to complete the 2D CFT story, using this map to just a single complex plane, you can use the fact that you know how correlators and partition functions behave on the complex plane to essentially fix the Rényi entropy, and it looks like this. So C is the central charge of the CFT, epsilon is a short distance cutoff that you have to deduce, and ANs are some constants that are scheme dependent. They depend on your regularization prescription. And if you can just continue this to n equals 1, and you get the entanglement entropy. And another powerful feature of this method is that you can use further conformal transformations to other geometries to compute various other entangling regions that are not entanglement entropies that are not just for an interval in a plane. And relevant for celestial CFT, you can perform a Weyl transformation to a unit sphere, and you find that the Rényi entropy for an interval on a sphere looks like this, where L is the great circle distance between the endpoints of the interval. Okay. Right, so how can we use this this fact that the uniformization map is the same as the cosmic string superrotation to learn about celestial CFT? So my working assumption is going to be that the partition function in the CCFT is equal to the partition function of my bulk gravitational theory. This is going to be what I mean by my holographic duality. And then, as basically always, because I don't know how to do quantum gravity, I will take a classical limit and write my partition function as the exponential of some on-shell action. And then because of this relation between the uniformization map and the cosmic string superrotation, this on-shell action will be the action for the solution that I wrote down on one of my first slides of this metric with the cosmic string. And yeah, just I didn't have a good place to put it, but the tension of this cosmic string is related to n, as I mentioned. And this is the same tension that shows up in Rényi entropy computations in ADS-CFT in this work by Gidon. Okay, so now if I assume this holographic relation between the partition function of the CCFT and the on-shell action, Rényi entropies become this in terms of the on-shell action. And I can rearrange this slightly and differentiate with respect to n and obtain this differential formula, which, apart from this factor of I, also appears in ADS-CFT and Rényi entropies. And it turns out this is going to be a very convenient way to compute the Rényi entropies, because this derivative of the on-shell action is easy to compute. So to do it, we first need to regularize the conical singularity that we have in the presence of this cosmic string. And we do this by cutting out a tube, a small tube around the string. I call the radius of this tube delta. And now if I imagine computing this n derivative of the on-shell action, that's like some variation. So the bulk contribution to this on-shell action integral should vanish, because by definition, I'm computing the action on the solution to the equations of motion, so a first variation should vanish. And also, if I have a well-defined variational principle, then any boundary contribution should also vanish. But the exception is that I could get a boundary contribution from this tube, because this isn't really a boundary of my space-time. It's just some intermediate regulator that I've put in. And this kind of argument and this approach has also been used to essentially derive the Ryutaki-Nagy prescription, ADS-CFT. Yeah?
Can you say what are the boundary conditions and the metric variations?
Well, so I'm being essentially agnostic about this. I'm just assuming that I set up some boundary terms to...
You can't be agnostic. Well, that's for which I'm on the center wrote them. I just don't remember.
Oh, no.
The explicit boundary conditions and metric variations.
No, I mean, their analysis is pretty general, because they just need a... Let's talk about it more after. I mean, so we have another approach to calculating this where we do assume some boundary conditions and we get the same answer, but I think to a certain extent we can be somewhat agnostic. Okay, yeah, and so this is one of our key assumptions, that the variation of these boundary terms vanish. Okay, so now let's go ahead and compute this variation. So I want to compute these boundary terms arising in this cosmic string spacetime, and because this metric is so horrible, I will perform more or less the same coordinate transformation that I mentioned before to put the metric in a much simpler form that looks like this, where I have these u and v retarded time coordinates, and this is like a flat slicing of Minkowski space. Okay, and then the integral that I need to compute reduces essentially to the area of this tube around the cosmic string. But the problem is, so this u and v, I need to integrate them from minus to plus infinity, so this is divergent, and I need to introduce some regulators. And I'm going to introduce some cutoffs that have appeared in other areas of the flat holography literature. So one is going to be that I will restrict the product of the retarded and advanced times in this complicated metric coordinate system to be less than the square of some long distance L, which I'm going to think of as some kind of infrared cutoff. And then the other one is a bit more natural perhaps to understand, which is just that I'm going to impose a near square plus cutoff, which I think of as a large R cutoff. So I'll restrict R to be less than some big RC. And then if you perform this coordinate transformation to this much simpler coordinate system, so the product of the retarded and advanced times is invariant, so this cutoff looks the same. But now I get a rather complicated looking cutoff on this V. That depends on Z1 and Z2. And it's also singular at W equals to 0 and infinity, which is essentially where my cosmic string reaches scribe plus. Okay. And because of this singularity, it turns out that the near scribe plus and near string cutoffs, removing them is not, the process of removing these two cutoffs does not commute. So I can't just freely take my near string cutoff to 0. Essentially what will happen is if I try to do that, my near scribe plus cutoff sort of grows and covers the whole string. So I'm going to need to maintain a finite near string cutoff until the end of the calculation. And this is different from in the ADS-CFT case where you take this near string or near brain cutoff to 0 and you get this Ryu-Sakinagi prescription. Okay, so I just need to maintain this delta. And if I then do the integrals with these cutoffs that I mentioned and maintaining this delta, I eventually get a Rényi entropy that looks like this, where this epsilon is some combination of these two cutoffs. So it's small both because this delta is small and this RC is big. Yeah, and so this Rényi entropy that I get, it takes the correct form that I expect for a 2D CFT on a sphere with some prediction for the central charge. It scales like the square of this infrared cutoff over Newton's constant, and it's also imaginary. So there's several features of this that look a bit strange. I'll talk about them in a moment, but this does match some calculations from other approaches that have appeared in the literature. So the two things that seem weird, one is the factor of I, so the imaginary central charge. This is sort of to be expected maybe because the celestial CFT is not unitary. A bit weirder is the fact that the central charge diverges as you remove this IR cutoff by sending L to infinity. Okay. But if you're familiar with the celestial CFT literature, you might also be asking yourself, why don't I get C equals 0? Because this is also something that's appeared in many papers before. As you might guess from how minimalistic this slide is, I don't have a good answer to this. My feeling is that somehow it does come down to these boundary conditions at infinity. In particular, most likely that these the boundary conditions that you impose on this this cutoff that comes from this L. But it could also be that maybe there's some holographic renormalization prescription that you need to remove this divergent thing. But I don't know how I would implement this. So it's something to be investigated in the future. And so in the last minute or so, let me just advertise some more results that will appear in the paper, and you can ask me about them later if you're interested, which is we extended what we did to higher dimensions. So the problem that we faced was that on the CFT side, we didn't have an analog of a uniformization map in higher dimensions. And on the gravity side, we don't have an analog of the finite superrotation corresponding to the uniformization map. But we needed to somehow construct an asymptotically flat spacetime with the correct conical singularity structure to describe Rényi entropy. And we did it using some ADS-CFT technology. So the first step was to go to hyperbolic slicing of flat space. So this is something that's been used quite a few times in flat holography. So you slice the interior of the light cone of the origin with hyperbolic slices and the exterior with de Sitter slices. And then on each of these hyperbolic slices, we use a map that appears in this paper by Cassini, Puerto Myers, and ADS-CFT to construct the necessary geometry. And on the de Sitter slices, we use an appropriate analytic continuation. And we end up with Rényi entropies that are appropriate for a spherical entangling region in a CFT of d dimensions. It turns out that the cutoffs are not singular in this coordinate system that we construct. So there's no issue with the cutoff limits, and you can send the near brain cutoff to 0 and get a Ryu-Sakinagi prescription. And the results that we get are consistent with the previous result that we had for d equals 2. something funny that comes up is that we find that there's no type A Weyl anomaly when D is a multiple of 4. Because this type A Weyl anomaly coefficient is supposed to show up in a universal term in the entanglement entropy in even dimensions, like the central charge in 2D. But rather than a 0 central charge in 2D, we essentially get 0 central charge in 4D instead. Okay. So that was everything I wanted to talk about. Let me just quickly run through my outlook. I already mentioned that finding C not equal to 0 seems like a problem. And there's many other things that you could explore. And multiple intervals I think would be quite interesting because when you have more than one interval, the result's not completely fixed by conformal symmetry, so it probes the theory a bit more. And you can just read these others because I think I'm out of time. So thanks a lot for your attention. Yes, I mean, so the factors of I just come from the mismatch in signature between the Lorentzian bulk and the Euclidean boundary. It's inevitable from this factor of I.
I think your supervisor didn't explain to you how bad this is. It's extremely bad.
Well, I mean, let's see. It's to be expected, right? Because
It's bad that you believe this.
okay.
Yeah, just like perhaps it's mirroring the same question, but like how do you justify when you're matching the partitions, you're at least subjecting some boundary conditions or something on one, right? Like you're saying there must be some matching that you have here, or there's some reason you believe it. Like is it at the level of symmetries, or is it at the level of like how are you justifying the green box?
How am I just? Yeah, right. So one sort of philosophy that we took was just that it's the extension of this relationship between scattering amplitudes and correlation functions to the case of zero particles, essentially, right? The partition function of the gravitational theory is like the vacuum to vacuum scattering amplitude, roughly, and so it should be like a 0-point correlation function in the CFT, which is also like the generating functional. I mean, this isn't new to us, I should mention. I mean, this has also appeared in other celestial holography papers.
But do they specify how the matching is? Do they specify on the matching?
Well, yeah, so this is the problem that we're faced, is that so far as I can see, they've been very vague about, let's say, boundary terms. I mean, you have like a very well-established holographic renormalization procedure for flat space, and then also boundary conditions. So one calculation that I didn't mention that we did do was we imagined, like, let's say just on this, let's see, on this large R cutoff that I had, let's assume we have, let's see, no, yeah, on this large R cutoff, let's assume we have Gibbons-Hawking, and then you end up with a divergence, a divergent action, which you can remove with some counter term. But then also, so this was following actually, so this paper by Ogawa and Takiyanagi, so like a paper on a wedge holographic approach to flat space. And so in that, in wedge holography, they essentially have some sort of end of the world branes, and they're sort of doing holography for the region between them. And so one of the end of the world branes is essentially on this cutoff L that we have. And they need to have some tension on the brane, and they work out the correct tension for like the sort of Neumann boundary conditions. And so we also place this, and if with all these boundary conditions, evaluating the action with this this funky cutoff here, we also get the same result for the Rényi entropy. So this is one approach where we did commit to boundary conditions.
Okay, so with that, let's thank the speaker again.